In July of 1965, the United States Air Force ran into a problem they weren't prepared for. American F-105 fighter bombers flying over the jungles of Vietnam were suddenly being swatted out of the sky by large surface-to-air missiles moving at around 3 times the speed of sound, Mach 3. The culprit was the Soviet-built SA-2 guideline missile system, and its eyes were a ground-based tracking system known as the Fan-Song radar. Stealth wasn't an option yet, so aircrafts were fully exposed to radar. They couldn't outrun the missiles, and their heavy fighter bombers definitely couldn't outturn them. But as aerospace engineers desperately analyzed the flight data, they realized that all they needed was to focus on disrupting the enemy's radar guidance systems instead of trying to outrun the missiles, which was even harder. They began strapping crude, heavy pods to the wings of their aircraft, devices like the QRC-160, filled with glowing vacuum tubes and analog transmitters that blasted raw, high-powered radio noise into the sky. It was a blunt, brute force tactic, but it worked. The Fan-Song radars on the ground were suddenly overwhelmed with blinding static. They didn't realize it yet, but these early engineers had just marked the beginning of modern electronic warfare. When analysts fully grasped the physics of what they were doing, they realized that screaming loudly into the radio spectrum was only the beginning. They saw that if you could perfectly measure an incoming radar wave, you didn't just have to scream at it. You could manipulate its phase, distort its Doppler shift, and send it back. This single realization was a paradigm shift in electronic warfare. Now, let's explore exactly what happened, the deep physics of how jamming actually works, and why electronic warfare dictates the survival of every modern military on Earth.
The hype makes it sound like magic, like planes are casting an invisibility spell over the battlefield. But in engineering, there is no magic, only the clever exploitation of physical constants. To understand how a single electronic warfare jet, like the EA-18G Growler, can mess with a multi-million-dollar air defense network, we have to revisit the math of detection. In our previous video on how radar works, we derived the single most punishing relationship in sensor physics, the inverse fourth power law. Remember, radar is a game of shout and listen. The radar dish sends a massive pulse of energy toward the sky. As that wave travels, it spreads out spherically. Its energy drops very quickly. It hits the target, and then that tiny reflected echo has to spread out and degrade again on its way back to the receiver. Because the signal has to travel to the target and back, the signal weakens by the fourth power of the distance. To put that into perspective, a ground radar might transmit a pulse of 1 million watts. But by the time that echo bounces off a fighter jet 50 miles away and returns to the dish, the receiver is listening for an echo measured in picowatts, roughly 1/trillionth of a single watt. This vulnerability is what the jammer exploits. An electronic warfare plane doesn't try to quiet its echo. It instead tries to act as an active transmitter. When the enemy radar sends out a pulse, the Growler sensors catch it, but instead of letting the pulse bounce off naturally, the Growler transmits interfering signals back at the enemy's radar receiver. And here is where the physics really favors the pilot. The enemy radar's echo has to make a round trip, but the Growler's jamming signal only has to make a one-way trip. It is only subjected to the inverse square law. This advantage gave birth to the first generation of electronic warfare, noise jamming. If an enemy was tracking you on a specific 10 GHz frequency, your plane would simply scream raw, disorganized radio energy at exactly 10 GHz. This is called spot jamming. If the enemy radar was smart and tried to change its frequency to escape the static, you could use barrage jamming, screaming across a massive swath of the electromagnetic spectrum all at once. But physicists soon realized that noise jamming had 2 fatal flaws. First, it acts as a beacon. The radar operator might not know your exact range or speed, but they know exactly what direction the noise is coming from. Modern missiles can be programmed to switch into home-on jam mode, acting like moths drawn directly to the flame of the jamming pod. The second problem is a key limitation known as the burn-through range. Remember,
The jammer's power increases by the square of the distance, but the radar's echo increases by the fourth power as the distance closes. This means that as the jet flies closer and closer to the radar dish, the radar's natural echo is gaining strength much, much faster than the jammer signal. Eventually, there's a specific physical distance where the returning echo simply overpowers the jammer. The static clears, the plane perfectly appears on the screen, and the missile is launched. If you wanted to survive inside the burn-through range, brute force was no longer enough. Noise wasn't enough anymore. You also had to deceive the radar. To understand deception jamming, you have to understand how a radar computer actually tracks a target. Once a radar finds a plane, it creates a tracking gate, a tiny digital box of time and frequency that surrounds the target. The radar stops looking at the whole sky and only looks inside that box, expecting the plane's echo to be there on the next pulse. By the 1980s, engineers realized they could steal this gate. They designed deception jammers. Instead of blasting static, these systems act as a parasite. When the enemy radar pulse hits the plane, the onboard computer captures the wave, analyzes it, and copies it perfectly. To break the enemy's range calculation, the jammer uses range gate pull-off. The plane sends back a perfect copy of the echo, but artificially delays broadcasting it by just a few microseconds. Early systems actually did this physically by routing the intercepted signal through tightly coiled spools of wire to slow it down before transmitting it back. To the enemy radar, this delayed echo looks completely legitimate, and it is vastly more powerful than the real skin reflection of the jet. The radar computer latches onto this stronger signal. As the jammer slowly increases this microsecond delay, the fake echo moves backward in time. The radar's tracking gate follows the fake echo, dragging it entirely off the real aircraft. The ghost target on the radar screen slowly drifts backward. When the enemy fires their missile, the radar guides the weapon into an empty patch of sky. To break the velocity calculation, the jammer uses velocity gate pull-off. Because the radar relies on the Doppler shift to calculate speed, the onboard computer catches the wave, slightly shifts the frequency, and beams it back. This artificial frequency shift tricks the radar into thinking the plane is suddenly accelerating to Mach 4 or stopping dead in midair. The tracking gate violently snaps, the missile's guidance computer tries to calculate an intercept for an impossible physical maneuver, and its lock instantly fails. As we moved into the 21st century, the analog era of electronic warfare died. The spools of delay wire and vacuum tubes were replaced by one of the most precise signal processing technologies in modern aerospace, digital radio frequency memory, or DRFM. With modern supercomputing, a DRFM jammer uses incredibly fast analog to digital converters. It doesn't just copy a wave, it digitizes the incoming electromagnetic pulse in a fraction of a nanosecond, breaking it down into raw binary code. Once the wave is digitized, field programmable gate arrays, FPGAs, inside the jet can manipulate the physics of the signal in ways that seem like science fiction. The ultimate application of this is active phase cancellation. To understand this, we look at the geometry of a wave. A radio wave has peaks and troughs. If you take two identical waves and line up their peaks, they amplify each other. But if you shift one wave exactly 180 degrees out of phase so that the peak of the first wave lines up perfectly with the trough of the second wave, their amplitudes add up to exactly zero. They destroy each other. When an enemy radar pulse hits a modern fighter like the F-35, its electronic warfare system instantly calculates the exact phase of the incoming wave. It then generates an identical wave, shifts it perfectly 180 degrees out of phase, and broadcasts it back in real time. When the enemy's radar wave and the plane's jamming wave physically collide in the air, they interfere with each other, which reduces detectability or confuses radar processing. The radar energy nearly ceases to exist. The enemy screen shows unreliable intel. This is one way electronic warfare can complement stealth. But DRFM isn't just used for hiding. It is used to fake reality. Because the DRFM system holds the exact digital fingerprint of the enemy radar, it can duplicate it infinitely. Instead of sending back one delayed echo, the computer can rapidly copy the wave, apply specific radar cross-section signatures to it, and beam back 50 simultaneous perfect echoes. To the enemy radar operator, there is no static. There is no warning that they're being jammed. Their screen suddenly populates with an entire armada of enemy aircraft, some looking like tiny drones, others looking like massive B-52 bombers, flying at different altitudes, speeds, and headings. The radar's tracking computers overload trying to lock onto a massive ghost fleet that doesn't actually exist, while the real aircraft slips through the airspace completely unnoticed. But the evolution of the electromagnetic spectrum is a perpetual arms race. Radar engineers haven't just been sitting still. As we covered in our previous video, modern radars use active electronically scanned arrays, AESA. They can change their frequencies hundreds of times a second in a pseudo-random pattern, a tactic known as frequency hopping. If the jammer doesn't know what frequency the radar is going to use next, it can't intercept and cancel the wave. So electronic warfare evolved again, entering the era of cognitive EW. Modern EW platforms now use artificial intelligence and machine learning to analyze the entire electromagnetic spectrum in real time. The AI studies the enemy radar's hopping pattern, tries to predict what frequency the radar will jump to next, and preemptively tunes its jammers to that exact frequency before the radar even transmits. Furthermore, these modern jets have turned their own radars into weapons. By focusing thousands of tiny transmit modules onto a single point in space, modern stealth fighters can beam highly concentrated streams of microwave energy directly into the antenna of an enemy SAM site. In some cases, high-power emissions can actually interfere with or potentially damage sensitive electronics. The physics we've discussed, the inverse square law, phase shifting, destructive interference, and digital radio frequency memory, are no longer just theories in a textbook. They are the invisible parameters that play a major role in modern air combat survivability. It's truly a strange shift in military history. In World War II, electronic warfare consisted of bomber crews physically throwing thousands of strips of aluminum foil out of the window to create false echoes. Today, it is high-speed signal processing, occurring at the speed of light, dictated by autonomous artificial intelligence and field-programmable gate arrays. The electromagnetic spectrum is becoming an increasingly important domain of modern warfare, and while the planes of the future will undoubtedly fly faster and strike harder, their ultimate survival won't depend on how well they fight, but on how perfectly they can manipulate physics.